Good morning everyone. Today my topic is about digital envelope detection. I am Jinaraj from ECE section second year. This is the PPT of analog and digital communication subject. Let's get into the topic. Digital envelope detector is used to estimate the instantaneous magnitude of zero mean fluctuating amplitude digital signals. Asynchronous half-wave envelope detection. This is the figure of asynchronous half-wave envelope detection. The figure 1 is the digital version of a popular envelope detector used in the analog world of amplitude modulation AM and demodulation in analog AM receivers. The job of this envelope detector is to extract the low frequency amplitude envelope signals from the incoming RF signal. Not all the signals waveform in the figure 1 appear to be continuous. Keep in mind that they are indeed discrete time numerical sequences, which are digital signals. From the figure 1, it is the input signal, and the input signal is given to the thresholding circuit, and then half-wave rectifier sinusoidal signal will be present at the output of the threshold circuit, and after passing to a low-pass filter, this detects the envelope of the digital signal. This is by using asynchronous half-wave envelope detector, and due to the harmonics generated by the half-wave rectification in the figure 1 and possible spectral aliasing depending on the system's fs frequency sampling rate, careful spectrum analysis of a half-wave rectifier sinusoid is necessary to help for you determine the approximate cutoff frequency of the digital low-pass filter. The simple detector is called asynchronous because it need not generate a constant amplitude copy of the incoming RF sinusoid has to some of the other detectors we will be discussing. Asynchronous full wave envelope detection. We can reduce the high frequency noise riding on the figure 1 detector output by performing full wave rectification as shown. In the figure 1 we have done half wave rectification. By using full wave rectification we can reduce the high frequency noise. Here the lowest frequency spectral harmonic at the filter input is 2 FC Hz, so that the harmonic is more thoroughly attenuated at the figure 2 low pass filter output compared to the first FC Hz harmonics at the figure 1 filter output. So by this using asynchronous full wave envelope detector, the output is clear without noise. The source circuit is asynchronous real square law envelope detection. In the figure 3 is the digital version of a popular square law analog envelope detection. Sometimes it is also called product detector. Here the spectral harmonics of the filter's input are the same as those of figure 2. Differences give a mathematical description of the figure 3 envelope detector. So this is the figure 3 where the RF is given to the product modulator and the low pass filter, and then square root, so that the square root output is the detected envelope. So this is the asynchronous real square law envelope detector, asynchronous complex square law envelope detector, and the digital envelope detector that is uses the Hilbert transform is shown in the figure 4. This detector is described in more in details and references. This is most interesting envelope detector. This detector's advantage that no low pass filtering is need to at the output, so the square root operation. However, I learned this only by using true of noise free signals in practical real world applications. The low pass filter I have included in the by this is the ideal one. So in the practical we should definitely use a low pass filter so that the noise will be reduces. This is the RF signal, and the this here we are using Hilbert transforms circuit also, and the output of the low pass filter is a detector clean envelope. The fifth circuit is asynchronous real envelope detection. Figure 5 shows an envelope detector that called asynchronous because the RS input signal is multiplied by the local oscillator signal whose frequency is FC Hz. The complicated part of this detector is that the FC Hz carrier frequency of the received RF signal must be regenerated within the envelope detector to provide a local oscillator cos 2 pi fc t in plus pi signals. Another complication is that the local oscillator output must be in phase with the input RF signal sensor. This is the required figure of synchronous real envelope detection and asynchronous complex envelope detector. The figure 6 envelope detector is computed with the complex valued version of the incoming signal. Same as the other, here we are using two low pass filters, and separately the signal is separated and then again summed and given to the square root circuit so that the envelope is detected at the output of the asynchronous complex envelope detection. This detector is asynchronous in operation because local oscillator of frequency need not be equal to the FC frequency of the incoming modulator RF signal, and F0 within 25% of the FC is acceptable as long as the low pass filter sufficiently attenuates spectral energy near FC plus F0 hedges. Because of the I of n and Q of n sequences are in quadrature, phase cancellation occurs in the adder such that only spectral energy in the vicinity of the zero edges appears at the adder's output. As such, this detector is very tolerant of the local oscillator frequency phase drift just so long as the local cosine and sine oscillations remain in the quadrature. Although I haven't seen it in the literature, it seemed to me that we can eliminate one of the filters in the figure 6 and implement that envelope detection as shown in the figure 7. So this is the figure 7. This is the input signal, which is modulator signal given to the two prog modulators separately. One is cos term and one is sine one, and given to the I of n and Q of n, and again given to the summer and then square root, so that the square root output is shown in the figure, and then this square root output is given to the low pass filter where particular frequencies are low frequencies are this low pass filter allows the low frequencies and attenuates all the high frequencies, so that from the low pass filter we can detect the envelope of the digital signal. Upon analysis of the figure 7 detector, I was surprised to determine that it is exactly equivalent to the figure 2 asynchronous full wave envelope detector. For applications where high accuracy is not needed, such as automatic gain control, automatic volume control, or amplitude shift keying, ASK demodulation, the figure 1 detector is attractive because it's so easy to implement. Equally easy to implement, the figure 2 detector has been used for process medical electromyograms, EMG signals. Rank of the detector performance from the best to worst. The asynchronous complex square law is the best one, and the asynchronous full wave detector is the second best, and followed by asynchronous complex, and the fourth one is synchronous real, and the fifth best one is asynchronous real square law. If you need an envelope detector in the real-time world applications, I suggest you to implement the several of the above detectors to see which one is optimal for your signals and your FS data sample rate. Thank you.